Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. And in this lecture, I will discuss the frequency of oscillation in the transient state. And this lecture is part of the lecture series on the course of power system operation and control. And consider a small change in the operating angle delta naught due to a transient disturbance by delta delta. So, if the initial power angle was delta naught, then after a small disturbance, the new angle will be delta, and that angle delta is equal to the previous angle delta naught plus the small shift in this angle. Similarly, as a result, the electrical power will also undergo slight modification, and PE naught was the original power before the disturbance, and after the disturbance, delta PE, that amount of difference of power has been added and new power is PE. So delta PE is the change in power and PE naught is the initial power at delta naught. So new power is PE, which is equal to PE naught plus delta PE. PE naught is equal to P max sine delta naught, and plus delta PE will come as it is. And since delta delta is small because the disturbance is very small, then delta PE over delta delta can be written as dPE over d delta. So delta delta is small and delta PE can be assumed linear. So delta PE is equal to dPE over d delta multiplied by delta delta. And dPE over d delta in this case will be equal to P max cos delta naught, right? So the derivative of this term will be equal to dPE over d delta, and it will be equal to P max cos delta naught, and delta delta will come over here. So PE naught plus delta PE will be equal to P max sine delta naught, and in place of delta PE we can write P max cos delta naught into delta delta. So this is our new PE naught plus delta PE, and we know that PM is equal to PE naught, which is equal to P max sine delta naught. So mechanical power is equal to the initial electrical power for a lossless system. And PM minus PE naught plus delta PE, or we can say PM minus PE is equal to minus delta PE, right? PM minus PE naught plus delta PE will be equal to minus delta PE because this PE naught is equal to PM. So PM minus delta PE will be equal to minus delta PE. So by mistake, I have missed a negative sign over here. So it is actually minus delta PE equal to minus P max cos delta naught into delta delta because delta PE is already evaluated in the previous step. So delta PE is equal to this value and minus delta PE will be equal to minus this value. So now we can put this equation in the swing equation, and 2h over omega d square delta over dt square is equal to PA, which is equal to PM minus PE naught. So 2h over omega d square delta naught plus delta delta will divided by dt square is equal to PM minus PE naught plus delta PE, right? And uh, PM minus PE naught plus delta PE will be equal to minus delta PE, and it is equal to minus P max cos delta naught delta delta. So this is our new expression, and here P max cos delta naught is called synchronizing power coefficient or stiffness. And we have already discussed in our previous lectures the synchronizing power coefficient or stiffness, which uh, gives us the stability of the power system. So let's put this value over here, and 2h over omega d square delta delta over dt square is equal to minus s naught into delta delta. So we can take this expression to the left hand side and we can divide the whole expression with 2h over omega. So it will become d square delta delta over dt square plus omega s naught over 2h into delta delta is equal to 0. So this is a second order differential equation, And in this differential equation, the frequency of undamped oscillation is equal to the square root of this term, right? Because if we remember the simple harmonic motion in our previous classes, then that equation 1, which is written over here, this is a second order differential equation, and this is analogous to simple harmonic motion. Simple harmonic motion can be mathematically expressed as f equal to minus kx, and f is equal to ma, so ma is equal to minus kx, and a is equal to d square x over dt square. So d square x over dt square plus k over m into x is equal to 0. This is the simple harmonic motion, and the frequency of oscillation in this case is equal to the square root of k over m. So omega is equal to k over m under root, and we can also evaluate the frequency. This is the frequency in radian per second. So we can evaluate the frequency in hertz, and we can also evaluate the time period. So in this case, the frequency of oscillation will be equal to omega s naught divided by 2h square root, and the frequency of oscillation in hertz will be equal to 1 over 2 pi omega s naught divided by 2h. So that is the expression of the frequency of undamped oscillation. And now we will discuss the critical clearing time and critical clearing angle, and we will evaluate the mathematical forms of these two terms. So suppose we have a power system and we have a generator connected to a transformer and then a bus. So that bus is connected to another bus with the help of a transmission line, and another branch of this bus is actually connected to the transmission line, but that transmission line is grounded mistakenly. So there is a line to ground fault in the second branch of this bus, right? So the output of this generator in this case will become equal to 0 because this branch of the bus is actually grounded. So the output voltage of this generator will be equal to 0, and as a result, the output power of this generator will also be equal to 0. But this generator is fed by a mechanical source of energy, but the mechanical source of energy is constantly present over there. So the input mechanical energy is present, but the output electrical energy is equal to 0. So let's read this: when a fault occurs, PE is equal to 0, but input PM is equal to constant. As the result, system shifts from point A to point B in the power angle curve. So this was the initial operating point of the generator when its electrical energy was equal to the mechanical energy. But after the occurrence of this fault, its output power will be reduced to 0 and it will move from point A to point B. So let's suppose the system has shifted from point A to point B, then the output power of the generator will be equal to 0. So the rotor of the generator will undergo acceleration and it will shift from point B to point C. So at point C, it is running at higher speed. Okay. So let's suppose that the fault is cleared at the point delta equal to delta 1. So at this point, we will assume that the fault is cleared and the generator must reach its output power equal to the input power, which is equal to PM. So at this point, the generator should operate. But since the rotor of the generator has accelerated during the occurrence of the fault, so the rotor of the generator is running at higher speed than the nominal values. So its output power will be greater than PM in this case. So the system will move towards this point E, and due to inertia, the system output power will increase further and it will shift from point E to point F. And after some sustained oscillations, the system will restore to its original operating point after the clearance of the fault, and it will be constantly operating at point A after reaching the steady state. Okay, and finally settle down to point A after some oscillations. So if clearing time is increased from T1 to Tc such that delta 1 is a delta C where A1 is just equal to A2, then any further increase in fault clearing time beyond TC would not be able to enclose an area A2 equal to A1. So again, this is the discussion of the transient stability limit, which we discussed in our previous lecture. And suppose in this case, this clearing angle delta 1 is increased to delta C, which is shown over here. And this is the case of a transient stability limit. And from this figure, we can say that any further increase in delta C will never make area A2 equal to A1. So in that case, the system will be unstable. So this is the limiting value of delta C at which area A1 is just equal to A2 and the system will be stable. And any further increase in delta C will make the system unstable. So beyond delta C, A2 starts decreasing and fault clearance cannot be delayed beyond TC. This limiting fault clearance angle delta C is called critical clearing angle and the corresponding time is called critical clearing time. So from this figure, we can say that delta max is equal to pi minus delta naught. This whole angle from this point up to this point is pi, and if we sub and this angle is delta naught, and here this angle is also delta naught. So if we subtract delta naught from pi, we will have delta max. So delta max is equal to pi minus delta naught. Let's evaluate this area A1, and area A1 is equal to this Pm minus 0 and integration from delta naught to delta C. So we will see this figure. And area A2 will be equal to Pe minus Pm and integration from delta C to delta max. So this is our area A2 and we can substitute Pe equal to P max sine delta minus Pm, and let's evaluate these integrals, right? So this is our area A2 and A1 equal to A2 gives cos delta C minus cos delta max equal to Pm divided by Pmax into delta max minus delta naught. So when we equate these two areas, there will be some simplification steps which I think the students can perform by themselves. And after doing rearrangements and simplifications, cos delta C can be written as this expression, and it is equal to Pm over Pmax pi minus 2 delta naught minus cos delta naught. So delta C, which is the critical clearing angle, is equal to cosine inverse of this expression, and this is the mathematical form of the critical clearing angle. Now we will derive the expression for critical clearing time, and for that derivation we have to consider the swing equation which is given over here. So d square delta over dt square is equal to pi f over h pm minus pe. Let's solve this second order differential equation, and during fault occurrence Pe is equal to 0. So this expression is equal to this value, and let's integrate this expression. So we will have d delta over dt equal to pi f over h pmt, and let's further integrate this expression. So we will have delta equal to pi f over h pmt square uh, plus k. So after further integration of this expression, this is the value of delta, which is the angle. So at t is equal to 0, we will consider this initial condition to evaluate the value of this constant k, right? So there is a mistake in this expression which I was observing. So the integration of this term will be equal to pi f over h pm t square divided by 2. So I have missed 2 over here, but this 2 has been written over here. So this mistake has been corrected in the next step, but you have to remember that there is a 2 as well over here. So this is delta. Now let's evaluate the value of this constant, and it will be evaluated by considering the initial conditions. And at t is equal to 0, we know that delta is equal to delta naught. So this is the initial time at which the fault has occurred. So at t is equal to 0, delta is equal to delta naught. And let's put this value over here. T is equal to 0 means this expression will be equal to 0 and k will be equal to delta naught. So the value of k equal to delta naught can be substituted in this expression, and then this expression can be simplified for delta c. So delta c will be equal to pi f over 2 h pm t square plus delta naught. So TC, which is the critical clearing time, can be evaluated by rearranging this expression, and it will be equal to the square root of 2h delta C minus delta naught divided by Pm into pi f. So this is the expression for critical clearing time, and I hope that lecture is understandable to you. So this is the case which I was discussing, that this is the transient stability limit, and any further increase in delta will make area A2 to be less than the area A1, and the system will be unstable. So critical clearing time and critical clearing angles can be realized by considering the case of transient stability limit. So that is all about our today's lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.